Hello students, in this lecture we're going to talk about vector fields. So let's try to get a little introduction for the vector fields. So we'll say that vector field is a function that maps points to vectors. So if we in 2D space, then our function of x and y would map it into the vector uv. And if we in 3 space, then our function of x, y, and z would map it into the u, v, and w as a vector. So we take a point and we map it into the vector. So what can we say about these vector fields? These vector fields are the fields that physicists discuss in their work, right? That is discussed in physics. So what kind of fields it could be? It could be gravitational, for example, fields. Gravitational. Could be electric fields. Could be magnetic fields. And since we have few physicists, that's probably an interesting topic for them. There could be few more here. I'll put 3 dots. Could go further. So we will just stick to one kind of this field. So we will limit consideration to fields that do not depend on time. Otherwise it would be too hard for us in this class. So now visualization. Is there a way to visualize them? Is there a way to visualize them? That's our question. So let's do a little bit of recall. So we recall that vectors by themselves have no specified start point. So vectors by themselves have no starting point. Right. Probably have no specified starting point, right? So what do we do usually with vectors? Usually the vectors in a vector field are represented graphically by drawing a vector u and v which is equal to f of xy. And the main question is where to put its tail. So with its tail at the point xy. So let's look at an example how we can do that. So for our example, let's take some vector field fxy that is given by x squared y minus 2xy. So we can write it in this format, or we can say that x squared yi minus 2xyj, if you want to write it in this way. So what would be f of 1, 2? F of 1, 2 will be, so we plug in 1 and 2, so we calculate 1 times 2 is going to be 2 here for the first component, and for the second component 1 times 2 is 2 times negative 2 is negative 4. So then you go to the xy plane, right, so you go to the xy plane, and so you go to the point 1 and 2. So that's your starting point. Alright, and your vector is 2, negative 4. 2, negative 4, so what does it mean for us? If this is 1, 2, 3, and this is 1, 2, negative 1, negative 2. So what we need to do, we need to go 2 units to the right and 4 units down. So 2 units to the right from this point. So we go 1, 2, and we go 4 units down. So it will end up over here at negative 2. And we connect this with a straight line. Mine is not really straight, but I will use a help of I don't want to do that. Alright. So just like this. Alright, so this is our vector tail is at the point 1, 2, and it's vector of 2, negative 4. So it goes 2 units to the right, 4 units down. So what would be the vector at 2 and 3? So at 2 and 3, let's do that. So 2 squared is 4. 4 times 3 is 12. So we're going to get 12. And if we plug in 2 and 3 over here, 2 times 3 is 6, times 2 is negative 12. So what will happen? It will go 12 units to the right, so we probably will not be able to fit it in. So it goes 4, 5, 6, 7, 8, 9, 10, 11, 12. So it goes to 12, and it goes to negative 12 over here. So suppose somewhere over here, negative 12. So the point will be, okay, over here. So, and we start in 2 and 3. So we start over here, and we go way down over here. Alright, and this is our vector starting at 2 and 3 and go to negative 12, to 12 and negative 12. All right, so that was this example. All right, obviously if we use 0, 0, we don't really move because 0 will give us 0 vector. So not really much fun. All right. So let's look at the next example. In the next example, we have the following vector field. F of x and y is equal to negative 1/2 y and 1/2 x. Or we can write it 1/2 negative yx. So then if we take f at 1 and 2 and calculate it, we're going to get 2 over 2 will cancel, so we're going to get negative 1. And if we plug in 1 over here, we're going to get 1/2. So let's try to plot it. All right, so 1 and 2. So if this is 1 and this is 2, so we're starting over here, and we go to negative 1. This is 1. This is negative 1 and 1/2. Negative 1 and 1/2. Right, so what does it mean for us? We go 1 unit to the left. Here I don't think I did it right. Let's redo this one. So we have to go 12 units down, right? 12 units down from 2, so we go to negative 10. And 12 units to the right from 2, this should be 14. Sorry about it. So we go 12 units to the right from 2, so we arrive to 14. And we go to 12 units down, that means we arrive to negative 10. So over here we moved 1 unit to the left, so we start over here, so we move 1 unit to the left and half of a unit up, So our vector looks like this. All right, but then if we continue with this problem, we can do the following. We can consider a so-called radius vector that starts at the origin and goes to our starting point, goes to 1 and 2. So our vector will go from the origin to the starting vector, to the starting point over here. So this will be our r vector. All right, and again, this point is marked by 1 and 2. All right, so now we're going to move a little bit forward, and we're going to consider r dot f of xy. Right, so since it produces a vector, we can take a dot product. So let's see what we can achieve. So since our function is given by this over here, and that's our starting point, this will be r, right? R will be denoted by x and y. So we have x, y, that's our r vector. This is our r vector. We can probably put a little arrow over here. So we put a dot. And what is our f of xy? Our f of xy is this, right? Is this. So we can say negative 1/2 y, 1/2 x. But then we can take 1/2 and put it outside over here as a constant. and we have xy dot negative yx. So we get 1/2. We have negative xy plus yx if we take a dot product, but this will be 0. So we have 1/2 times 0, which is 0. So what does it mean for us? That these vectors are orthogonal, right? That's what it means. So we say therefore R and the vector field are orthogonal. Right? So now, what would be the magnitude of x and y, of f of x and y? The magnitude of this function you can always write as as 1/2 of so 1/2 squared and square root will give us 1/2. So we're going to get y squared plus x squared. It should be 1/4 here, but we can take it out and put it here as 1/2. So it's going to be 1/2, but as you can see, this is exactly the magnitude of xy. Exactly the magnitude of xy. Alright, and this is our vector r actually here, so we can think of it as 1/2 magnitude of r. So we can do this part. So that means what? That this function f produces tangent vectors to radius vectors. So let's look at the following example. So if we take our example like this, if we take our f to be equal to xy divided by the square root of x squared plus y squared. So basically this function takes any vector and returns a unit vector. Returns a unit vector in the direction of the vector starting at the origin and ending at xy. Right. So it's always a unit vector. So basically, if you have a point over here, all right, then we'll have a unit vector going in the direction of this line over here, right? And if we have a point over here, then our unit vector will look up in this direction. All right, and so if you have a point over here, then you will have a unit vector sticking out in this direction. And obviously one will be here, and they're all unit vectors. All right, if we look at the different example, if we take a function g of xy to be negative xy over the square root of x squared plus y squared, it is very similar to this one, but it has a minus here. So what does it mean? That means that g does the same thing, as f. Maybe we'll mark it with the vector signs, except all the vectors, or the unit vectors, point towards the origin. So if we try to visualize it for the function g, so if you have some line going through the origin, then your unit vector will point into the direction of the origin, right? If you have some vector, unit vector will point towards the origin, and your unit vector will point towards the origin. So we'll have something like this. Alright, so what's the next idea? To move a little bit forward and think like this. So let's recall a little bit. Let's remember what gradient is. So if we take a gradient, it gives us partial f with respect to x, partial of f with respect to y, right? Some people would like to write it as f sub x of xy and f sub y of xy. So at any point xy. So what can we say? We can say that the gradient of f points in the direction of greatest ascent, right? Of greatest ascent of f. So interesting property, right? Interesting property is that it is not surprising that vector fields that are themselves gradients of other functions, have some interesting properties. So let's look at this idea. So let's consider gravity. Consider gravity. So how we can simplify it? We can say that if we relax how we speak about it, so loosely speaking, the attraction of two objects due to the masses, right? Due to the masses of the objects and the properties of the space in which the objects are embedded. So usually it's given by this rule. So we have force F is equal to gravitational constant m sub 1, m sub 2 divided by r squared. And since this is a vector here, we need a vector over here since this is a scalar, right? Since this is a scalar. So what is what here? G is some constant. What else is here? M1 and M2 are masses. What else do we have? We have R. R is a separation distance. Separation distance of the masses. And the last thing in this vector U is a unit vector. Pointing from one mass to another. Pointing from one mass to another. Right. So suppose we create a system of coordinates. So we're going to suppose that M1 is located at the origin, so 0, 0, and 0. And M2 at x, y, and z. So what would be our vector r? Our vector r is really easy, just x, y, and z. Right, then the magnitude of r is the square root of x squared plus y squared plus z squared. So what would this be the magnitude of f? The magnitude of f is let's look back to the formula. This is a constant, this is a constant, this is a constant, and r squared, it's the magnitude itself. So we can say g is a constant, m1 is a constant, m2 is a constant, and the magnitude of r squared is a constant, and the magnitude of u is 1, since it's a unit vector. Alright, so that's that's what we get here. So basically we get G, M1, M2, and loosely people often write R squared like this. So now the direction of the force. The direction of the force from the point of U of M, point of view of M1 is negative R over the magnitude of R. That would be our unit vector. And again, if you're looking from M1, it attracts the other object right towards itself, like we just discussed function G. Alright, so we can define big F of x, y, and z to be G M1 M2 over magnitude of R squared times the unit vector negative R over the over the magnitude of R. Alright, and so finally we get negative G M1 M2 R over the magnitude of R cubed. So let's define something based on this idea. So what would be our definition? Our definition would be a vector field F in 2 space or 3 space, in 2 space or 3 space is said to be conservative, if it is a gradient of a scalar field. So we define the conservative vector field. So and this scalar field is usually called phi. That's the usual name for it. So what do we mean by this? We can say that if we can define f to be equal to the gradient of phi. All right, and the function phi is called the potential function for f. All right. So another definition that we can produce from our discussion, we say that if R is a radius vector in 2 space or 3 space, and if C is any constant, let's say is a constant, it's better, is a constant, then a vector field of the form f of R is equal to C divided by magnitude of R cubed times R is called an inverse square field. An inverse square field. And some people call it inverse square law. Some people call it inverse square law. Some people call it like this. All right, what else do we have to say? Probably a good place to stop this lecture. See you in the next one.